So let's keep solving these. So again, we're simplifying. We'll combine the outside and the inside terms. So we get 18. 2 times 9 is 18. And then 8b cubed times 18b. So 8 times 18. 8 times 10 is 80. 8 times 8 is 64. 80 plus 64 would be 144. And the b cubed times b would be b to the fourth. Now, we can actually simplify this one pretty quick, since we can break it up into the square root of 144 times by the square root of b to the fourth. And root 144, that square root is 12. So you just get 18 times 12. And then the square root of b to the fourth, we'll just break it up into b squared times square root of b squared, since each of these is just b. The square root of your variable squared just comes out to be the absolute value of that variable, but we always assume b is positive. So let's do this. 10 times 12 is 120. 8 times 12, you get 80 plus 16 would be 96. So 120 plus 96 would be 216. And you get b here and b here, so you get times by b squared. So this is what you'd put in the box, 216 times b squared. It looks like all the square roots were able to go away. And moving on, do a couple more of these just so that you get a lot of practice. So with this one, nothing's on the outside, so we're just going to simplify the insides altogether. So we have the square root of 24 times 40. We can just do 4 and 24 is 96. And adding a 0 to that. And then b cubed, b squared, and b squared. So that's b to the fourth, and b cubed times b to the fourth would be b to the seventh. So we've got an odd amount of b's, which means one of them is going to be left on the inside. And then 960, we're going to have to make a tree. So let's do 960. And we know it's 10 because it ends in a 0 times 96. 10 is just 5 and 2. 96 is 24 and 4. And 24 is simply 2 and 12. 12 is 3 and 4. And 4 is 2 and 2. Likewise, this here is 2 and 2. So this was a pretty big tree. So lots of branches. And I like to circle them all at the end. Basically, where do all of these chains actually end? So then 960, let's see, we've got 1, 2, 3, 4, 5, 6 2s. So it's 2 to the 6th. And then we've got 1, 3, and 1, 5. So times 3 times 5. And you can double check that with your calculator. And for our variable expression, since we can break this up into root 960 times root b to the 7th, this root b to the 7th we can look at separately. And essentially just split it into a bunch of b squareds multiplied together, and then we'll have that lone b at the end. So this is root b squared times b squared times b squared times b, since in total you still have 7 b's, it's just broken up. And then each of these b squared terms I'm going to put in their own square root. So we have a product on the inside, which means we can turn this into a product of square roots. And each of these is just going to be b. So b times b times b, so you get b cubed times by the square root of b. Let me just rewrite that since it's a little bit sloppy. So b cubed times root b. And so let's deal with both the numbers and the variables together now. Let me do it right here. So this is equal to root 960, but remember 960 is just 2 to the 6th times by 3 times 5, and I'm going to recombine those to make 15 because 15 is not a perfect square, and so it's going to be left behind anyways. And then you have the square root of b to the 7th, which we figured out was b cubed times root b. And just to make it clear, that ends there, so b cubed is on the outside. Now, 2 to the 6th we can break up. Let's do that up here. 2 to the 6th is really just 2 squared times square root 2 squared times square root 2 squared. Or it's the square root of 64. So this is 2 times 2 times 2, which is 8. Or it's root 64, which is also 8. So that's going to simplify. We're going to be able to get 8 on the outside, and 15 will have to stay on the inside. So in the end, you get 8 b cubed. So that's all our outside stuff, and then what's left on the inside is root 15b. And so this is what you'd actually put in the box. 8b cubed times the square root of 15b. And let's do one final problem just to get a little bit more practice. Again, we're simplifying these square root expressions with variables. And with this one, we don't have any numbers on the outside, so let's just combine all the square roots together. So you get the square root. So out of the z's, there are, it looks to be 6 of them, z squared, and z cubed. So you get z to the 6th. And then you have 1 times 30 times 35. So 3 times 35 would be 105. And then we'll just add a 0 to that. So 105 with a 0, so 1050, z to the 6th. And let's make a tree with the 1050. And we know that it's just 105 times 10. 10 is just 5 and 2. And 105 is 35 and 3. And 35 is 5 and 7. So 1050 looks like 5, 7, 3, 5, 2. It's got two 5s. Well, let me do 2 times 3 times 5 squared times 7. So this is the prime factorization of 1050, and we can use that to help simplify it under the square root. So this will be equal to root 1050, but that's just 2 times 3 times 5 squared times 7. So I'll write 5 squared first, and then 2 times 3 times 7. So all three of these will have to stay on the inside since none of them are perfect squares. So when I rewrite it next, I'm just going to multiply these out. 6 times 7, and just rewrite 42. And then we have times the square root of z to the 6th. But remember from an earlier problem, when you have an even amount of these in a square root, when you actually pull them out, you're going to cut it in half. So we'd end up with z to the 3rd on the outside of the square root. But to make more sense of that, you always want to think things through in terms of basic principles. And for this one, for instance, we can just rewrite it as root 5 squared times root, that's 6 times 7, which is 42. And then over here, the z to the 6th. So from basic principles, I'm going to rewrite this as z squared times z squared times z squared. Since now I can break it up into individual square roots. Root of 5 squared is just 5. And then root 42, we'll have to keep that. That won't simplify. And then over here, each of these can be its own square root. So root z squared times root z squared times root z squared. And then each of these, the square root and the square cancel each other, and you just get positive z. Or really, technically, you get the absolute value of z. But we're going to assume z is positive, so we can drop the absolute value bars. So we have 5. And then this will be z times z times z. So 3 z's, or in other words, z cubed, times by the square root of 42, since that cannot come out. So 5z cubed root 42 is what we'd actually put in the box here.